begin. Okay, so first of all, okay, let's begin. So first, I would like to introduce Lequan Yu, and I'm very pleased to invite him to give us a talk on his very interesting research about medical imaging analysis with data efficient deep learning. And I would like to give you a short introduction of Lequan. Lequan is currently a postdoctoral researcher at University of Stanford, and he received his PhD degree from computer science at Chinese University of Hong Kong in 2019. And his bachelor degree was from Zhejiang University. And he also experienced the research internships in NVIDIA and Siemens Healthcare. And his research interests are developing advanced machine learning and deep learning methods for medical imaging analysis and reconstruction. He has won CUHK Young Scholars Thesis Award in 2019 and has also won the Best Paper Award of Medical Imaging Analysis (MICAI) in 2017, and the International Workshop on Machine Learning and in Medical Imaging in MICAI 2017. His first authored TMI paper is classified as highly cited paper by ESR, and his current Google Scholar citations has reached 4,000 plus with H index 26. And without any further ado, all yours, Lequan.
Yeah, okay. So thanks, Damien, for the introduction. And thank you all for the comments. So it's a very pleasure to present my works on medical image analysis. Okay, we are at the moment of artificial intelligence, and we can apply deep learning to solve different applications like image perception, autonomous driving, natural language processing, and robotics. Besides the above field, AI in healthcare is another giant opportunity. There is a huge physician shortage in the future, and the AI in healthcare has become an emerging topic to eliminate this problem. For example, the new item AI in healthcare was created in Wikipedia, and in RSAN conference, people talk about how AI will empower radiologists to provide better patient care. As an interdisciplinary research area, both the medicine and the engineering researchers are interested in this topic. The top medicine journals published articles to discuss how AI can be used to solve the healthcare problems, like the New England Journal of Medicine, the Lancet, and Nature Medicine. Meanwhile, the engineering researchers also interested in how to adapt AI in radiology and healthcare problems. Besides the academia, the industry has also involved in this direction. Google has collaborated with Mayo Clinic to provide the healthcare delivery. So in current healthcare procedures, medical imaging is a critical step, and more than 70% clinical decisions depend on medical images. Using AI can actually improve the entire medical imaging workflow, from the image acquisition to prognosis. And my research focuses on a key part of this research area, which is AI for medical image analysis and medical image reconstruction. Automatic medical image analysis, like automatic anatomic structure segmentation, computer-aided disease or cancer diagnosis, and lesion detection, is beneficial to computer-aided diagnosis, assessment, and therapy. And using deep learning can largely improve the accuracy and efficiency of disease diagnosis so that it can advance disease diagnosis and therapy. However, there are a series of challenges for deep learning-based medical image analysis. From the image level, we can see the medical image has a series of characteristics. For example, for the lesion detection task, we can see the true lesions and the false positives are very similar. And for the medical image segmentation task, the image contrast of the medical image is very low. This is the ultrasound image, and this is the prostate. We can see the boundaries of the prostate is very ambiguous. And another is most of the medical image are high dimensional, like the 3D MRI and CT volumes. In this case, we need to design effective method to handle the 3D data. And in another aspect, the deep learning system is data hungry. Generally, it needs a large amount of training data set to achieve good performance. For example, most of the computer vision systems are pre-trained on ImageNet, and ImageNet includes more than 1 million images. And the state-of-art language model BERT was pre-trained on the whole English Wikipedia. It includes more than 2,500 words. While in medical imaging domain, the training dataset is limited because some diseases are small naturally, so that it is difficult to collect lots of samples. And the data regulation and the privacy issue further prevent us building a large-scale dataset. Another is different from the natural image. The annotation in medical imaging domain needs for domain expert. That means only the experienced doctors can annotate the reliable annotation. So in this case, it is more harder and expensive to acquire a large-scale labeled dataset. Moreover, medical images are often from different scans hospitals and scanned with different time points. And one basic assumption of deep learning is that the training and the testing dataset are from the same distribution. The domain shift between the training and the testing dataset would lead to performance degradation. So in this case, how to handle with the multi-set heterogeneous dataset is another challenge. As we mentioned in the above challenge, the question of my research is how to build intelligent deep learning systems for medical imaging tasks. And in my research, we focused on designing such systems by proposing data-efficient learning strategy so that we can effectively utilize the limited dataset to design effective methods for medical imaging tasks. And in this talk, I will discuss about our data-efficient learning works to utilize different data sources for robust medical image analysis tasks, like the semi-supervised learning to utilize the unlabeled data, and the multi-modality learning to utilize cross-modality data, and the multi-set learning to utilize the multiple heterogeneous dataset. And if we have time, I will also briefly introduce my very recent work about how to incorporate domain knowledge into AI models for medical image reconstruction. First, I will present our semi-supervised learning work. Although the labeled data is expensive and limited in medical imaging domain, the unlabeled data is generally abundant, so that we study the semi-supervised learning for medical imaging tasks. And the semi-supervised learning aims to reduce the need for labeled dataset by additionally utilize the unlabeled dataset. Recently, most of the semi-supervised learning is based on the consistent recognition, which encourage the network prediction to be consistent and different perturbations for the same input. However, most of the previous semi-supervised learning is focused on image classification. So in our work, we first propose a semi-supervised segmentation framework. This framework is based on the teacher-student strategy. So we have a student model and a teacher model. The network architecture of the two models are the same. And for the unlabeled data, we add different noise into the input data and feed the noise the input into the student model and the teacher model so that we can get two predictions. Since these two predictions are from the same input, their prediction should be very similar. So therefore, we calculate a voxel-wise consistent loss to minimize the difference of these two predictions. And this loss can guide the network to learn meaningful information from the unlabeled data. And actually, in this framework, we can regard the output from the teacher model as the teacher target. The student model wants to learn from the teacher target. And in order to improve the quality of the teacher target, we also adopt the self-ensemble strategy. That means the weight of the student model was trained, but the weight of the teacher model is not trained. It's the exponential moving average of the student model. However, we don't have labels for the unlabeled data set. The teacher target on the unlabeled data may be reliable or noisy. So if we directly learning from those noisy targets, it would reduce the overall performance. And to solve this problem, we propose to use uncertainty estimation to eliminate this problem. Uncertainty estimation is widely used to evaluate the model's confidence. Therefore, through uncertainty estimation, we can know what the model doesn't know, so that we can find those unreliable targets and let the student model only learning from those reliable teacher targets. So specifically, given the input image, the teacher model not only output the teacher target, but also estimate an uncertainty map with the Monte Carlo dropout. Then we use the uncertainty map to guide the consistent loss calculation so that we only minimize the difference for those confident or certainty voxels. And in this case, we can reduce the inference of those unreliable targets. And the total objective function of the whole framework is the combination of supervised loss on labeled data and the unsupervised consistent loss on unlabeled dataset. And for the experiment, we use the benchmark left atrium segmentation dataset to evaluate. And for the experiment setting, we use 20% scan as labeled data and the remaining scan as unlabeled data. So in this table, we first show the network trained with the 16 labeled scan and 80 labeled scan, so which can be regarded as the low-line and up-line performance of the whole framework. And the last row shows the performance of our method. Compared with the low-line performance, we can see that our semi-supervised method achieved a high dense performance than the low-line by utilizing the unlabeled data. And the performance of our semi-supervised method is also approaching the fully supervised upline. And we also list the performance of other semi-supervised learning methods like self-training or pseudo-label-based method. And the GAN-based method, we can see that our semi-supervised method outperforms this state-of-art semi-supervised learning method. And we show some segmentation examples and the estimated uncertainty. So from the visual example, we can see that our semi-supervised method have a large overlap with the ground truth compared with the supervised only baseline. And our method also reduces the false positives by utilizing the unlabeled data. And from the estimate uncertainty map, we can see that generally the network has very high uncertainty near the boundary regions. So this is similar with the natural image observation. So generally, the network has high uncertainty for the boundary pixels. And in our following work, we further propose a relation-driven self-supervised learning framework for medical image classification. Because the traditional consistency-based method only rely on the individual consistency, so they only minimize the difference of the samples case by case and ignore the relationship among different samples. But in medical image diagnosis procedure, sometimes the doctors would refer previous similar samples for reliable decision. So inspired by this observation, we wanted to use the sample relationship of different samples to boost the semi-supervised classification performance. Therefore, we propose a sample relation consistent scheme. So we can see that in this scheme, besides minimize the difference of individual samples, we also minimize the difference of the sample relationship. This figure shows the framework of our method. We can see this framework is also based on the mean teacher-based framework. And this, given the input image, we feed it into the student model and the teacher model so that we get two predictions. And like the traditional method, we use the individual consistent loss to minimize the difference of these two predictions. And besides that, we also add our proposed sample relation consistent scheme. Specifically, we calculate a sample relation metric from the features for student model and the teacher model. And then we also minimize the difference of the sample relation metrics. And specifically, we model the relationship among different samples with the gamma metric, so that given a input mini-match of n samples, we calculate a n by n correlation metric. Actually, this metric shows the similarity of different samples. And our proposed sample relation consistent scheme minimize the difference of the relation metrics for the teacher model and the student model. And this scheme can encourage the network to learn more robust and discriminative representation by utilizing the high-level semantic informations. And we evaluate our method on the single label scan linear analysis task and the multi-label chest X3 classification task. So our method achieved very good performance for single label and multi-label classification tasks. And besides the semi-supervised learning, we also studied the multi-modality learning to utilize the cross-modality data. Because in medical imaging domain, multi-modality data are widely available. For example, the different MRI images were used to show the tumor structures in brain imaging, and the CT and MRI image are used to provide anatomical information of the cardiac structure. Although the different modality data shows the difference in the appearance, but they reflect the same anatomical information. So based on this observation, we want to study how to exploit the cross-modality data to eliminate the annotation scarcity. Specifically, we wanted to study if it is possible to utilize the labeled MRI data to boost the CT segmentation. And in this problem, the key challenge is how to utilize the shared knowledge of different modality data, like the CT data and the MRI data. And in our recent Truba AI paper, we propose a novel mutual knowledge distribution scheme to do that. So given two different modality data, like the CT data and the MRI data, we first train two segmentation networks, and each segmentation network learns the knowledge from each modality data. And at the same time, the two segmentation networks are also trained with mutual guidance, so that each network can also learn the knowledge from another modality. And to achieve the mutual guidance, we adopt the knowledge distribution scheme. The basic idea of knowledge distribution is to let one network to imitate the output from another network, and the original knowledge distribution is proposed for network compression. Specifically, we have the labeled MRI data and the labeled CT data, and we want to train a segmentation network to segment the CT image. To do that, we first propose an image alignment module to reduce the appearance gap of the CT image and the MRI image. That is, we use a generative adversarial network to translate the MRI image to the synthetic CT image. And then we use the proposed mutual knowledge distribution scheme to train two segmentation networks. And each network can utilize the knowledge or information from both two different modality data. And in the testing phase, we feed the CT image into the two segmentation networks and use the ensemble of these two predictions as our final prediction. And we show the performance of our method on the multi-modality whole heart segmentation benchmark dataset. This dataset has a paired MRI image and CT volumes, and it provides the anatomic annotation for the cardiac substructures. And the first experiment is the MRI to CT experiment. So we wanted to utilize the MRI data to improve the CT segmentation. And in this table, we first show the performance of the baseline. In baseline, which means we only use the labeled CT to train the network. And we also show the performance of our method. So compared with our method and the baseline, we can see our method achieved a high mean depth than the baseline. So it shows the effectiveness of utilizing MRI data to boost the CT segmentation. And in this table, we also compared our proposed method with other multi-modality learning-based methods, like the fine-tuning. In fine-tuning, we first train the network with labeled MRI and then fine-tune it with the labeled CT. And the joint training. In joint training, which means we directly mix the MRI data and the CT data and train one segmentation network. So we can see that our method achieved better performance than the fine-tune and joint training-based method. It shows that our method can effectively utilize the shared knowledge of CT and MRI. And in this figure, we show some synthetic CT image and the real MRI image. So we can see that the heart structures are very clear and well preserved during the MRI to synthetic CT translation. And we also conducted another experiment by utilizing the CT image as the assistant modality, MRI as the target modality. And in this case, we also compared our method with the MRI supervised only baseline. In this case, our method also outperforms the MRI baseline. It shows that we can also utilize the labeled MRI data to boost the CT segmentation. So generally, we can say the benefit of our proposed mutual knowledge distribution is bidirectional. So far, we have introduced two different strategies to eliminate the annotation scarcity. That is the semi-supervised learning to utilize unlabeled data, and the multi-modality learning to utilize the information from a related modality. So a natural question is whether it is possible to combine these different strategies so that we can utilize all available data sources for more robust segmentation. For example, for the CT image segmentation, so can we simultaneously utilize the labeled MRI and unlabeled CT to improve the CT segmentation? And in our recent Mikan and TMI paper, we studied this problem and we show it is possible. We propose a two-teacher framework for annotation efficient cardiac image segmentation. So as shown in this figure, we have three types of dataset in this problem setting, that is labeled CT, labeled CT, and labeled MRI. And we wanted to train a network to segment the CT image. So very similar with the last work, we first use an appearance alignment module to translate the labeled MRI to synthetic CT to reduce the appearance gap. And then we train a two-teacher framework to utilize the three different types of dataset. So we use an intra-domain teacher to learn the knowledge from the synthetic CT or the labeled MRI. And we also train an intra-domain teacher to learn the knowledge from unlabeled CT. And we also have a student model. The student model directly learning the knowledge from labeled CT, but also grasp the knowledge from the to teachers with knowledge distortion. So in that case, the certain model can utilize the knowledge from these 3 different data sets. And we also evaluate our method on the multi-modality whole heart segmentation dataset. To the best of our knowledge, we are the first to study the semi-supervised multi-modality learning, so that we compared our method with the unsupervised domain adaptation, multi-modality learning, and semi-supervised learning. So we can see that on the average mean depth of the different substructures, our method achieved the best performance. So it shows the feasibility of simultaneously utilize unlabeled data and cross-modality data for improved segmentation. And we also show some visual results for comparison. This is the low-level performance. That means this is the performance of CT supervised only. And this is the unsupervised domain adaptation. This is the multi-modality learning, semi-supervised learning, and our method. And this is the ground truth. So compared with the unsupervised domain adaptation and other methods, we can see that our method can generate very smooth predictions and also reduce some false positives compared with the baseline. Next, I will present our works on the multi-set learning. So as we mentioned above, the medical images are often from different hospitals or scanned by different devices, so that it has some discrepancy among different datasets. And in this figure, we show the MRI prostate image from 3 different datasets. We can see that the appearance difference of different datasets. And because generally we need a large amount of training data set to train a good network to achieve very good performance. But generally it is very hard to collect lots of samples from a single set or single hospital to train the neural network. So that it is very meaningful to aggregate the multi-set data set to train a neural network for more robust medical image analysis. But as shown in this figure, the images from different datasets have some heterogeneity, and the heterogeneity of different datasets would lead to challenges when we combine the dataset from different sets. And to show this problem, we conducted an experiment. In here, we have the 3 datasets, and we first train a neural network with each dataset and test it on the same dataset. For example, we train a neural network with the training sample from dataset A and test it on dataset A. This is the DICE performance. And we also train a segmentation network with the images with dataset B and test it on dataset B. This is the performance. So generally, when we use the separated network, the average performance on the 3 dataset is 20.56. However, if we directly combine the images from different datasets and train one segmentation network to segment the image from all the datasets, we can see that the average DICE performance is only 20.25. It's lower than the separated training. It shows that if we directly mix the images from different datasets, it would cause to limited improvement or even would slightly reduce the performance of the individual training. This is due to the heterogeneity of different datasets, because generally the network needs for a very well-aligned distribution sample to achieve good performance. So therefore, in our recent work, we propose a multi-set network to jointly learn a universal network from different datasets. As shown in this figure, we have S different datasets in the training data pool, and we want to train a universal network to segment the images from this different set. And to do that, we propose a multi-set network. We call this network as a multi-set. So generally, we can say the network follows the common used encoder and decoder framework. And in the network backbone, we adopt the domain-specific batch normalization. That means we calculate the mean and the variance for each set and normalize the features for each set sample individually. So that in this case, we can overcome the interset heterogeneity. And to better learn the shared knowledge of different datasets, we also proposed a novel learning technique that is the multi-set guided knowledge transfer. Specifically, we add some auxiliary branches into the network, and each branch learns the knowledge from each set data. And then we also have a universal decoder, and we use the knowledge distillation mechanism to translate the knowledge from the auxiliary branches to the universal decoder, so that the universal decoder can better learn the shared knowledge of different set image. And in the testing phase, we can discard the auxiliary branches and only preserve the universal encoder and the universal decoder. We use the previous mentioned prostate dataset to conduct the experiment. And we show the performance of the separated training. That is, we train a network on dataset A to segment the image from dataset A, and train a segmentation network on dataset B to segment the images from dataset B. And this is the mean DICE performance. And we also show the performance of joint training. That means we directly mix the image from ABC and train one segmentation network. And the last two rows show the performance of our method. So we can see that the final performance of our method is better than the separated training and the joint training. And when we see the performance on each dataset, we can see our method consistently improves the segmentation performance on all of the dataset. And when we compare the performance of the last two rows, because this is the performance of, we only use the domain-specific batch normalization, and this is our final result. Besides domain-specific batch normalization, we also use the proposed multi-set guided knowledge transfer. We can see our final result is better than the DSBN, so it shows the effectiveness of the multi-set guided knowledge transfer. And we also show other multi-set or multi-domain learning-based method. Again, our method outperforms this state-of-the-art multi-set based method. And in our another TMI paper, we study a more general setting of multi-set learning. Because in the previous work, we assume the annotation of different samples of different sets are the same. Because, for example, we assume that in the three different datasets, we only want to segment the prostate, and both of the images have the prostate annotation. But in a more practical settings, the dataset, the images from different datasets may have different annotations. For example, in the chest X-ray disease diagnosis, we show the commonly used NIH and the chest expert public dataset. So we can see that the label annotation of the NIH dataset and the chest expert dataset are different. They annotate the different disease, and they have some common annotated disease and some separately annotated disease. So we can see the discrepancy between different datasets can include the appearance discrepancy and the label discrepancy. And in our previous work, we only solved the appearance discrepancy, not consider the label discrepancy. And in this work, we propose a framework to handle with the image discrepancy and the label discrepancy at the same time. Because this is, firstly, we formulate the framework as a multi-head framework. Because this is a multi-label classification. So we use each head for each to classify each disease or each label. So that in this case, we can handle with the partial label problem. For example, if the internal dataset has the annotation for the 4 diseases, we can calculate loss for corresponding 4 heads. And for another dataset, we can also calculate the loss for the corresponding head. And to handle with the image or appearance discrepancy, we use the adversarial learning strategies. But we propose a task-specific adversarial learning. That means for each common disease or for each head, we use the domain discriminator to encourage the network generate the common features for the images from the 2 datasets. Because as we said, the label annotation for the 2 different others are different. So that in some diseases there have unlabeled cases. For example, because the fracture we want to classify whether the image has the fracture. But in the external dataset, we have the fracture labels. But in the internal dataset, we don't have the label for the fracture. So that there is very similar. So for the fracture classification, this images from the internal domain actually as unlabeled. So that we also propose a semi-supervised learning strategy to utilize those unlabeled dataset. And another very important directions in multi-set learning is domain adaptation and generalization. Because we said different dataset has domain gap, and this domain gap would lead to domain shift among different dataset. For example, here this is the founder's image. And we can see that we want to segment the optical disc and the cup from the founder's image. So we can see if we train and test the network, if we train the network on dataset 1 and test it on dataset 1, the performance is very good. And if we train the network on dataset 2 and also test it on dataset 2, the performance is also very good. However, if we train the network on dataset 1 and test it on dataset 2, the performance is very bad since there is a domain shift among these 2 different datasets. So this observation motivates us developing domain adaptation and generalization method. So in the setting of domain adaptation, so we have 2 domains. One is source domain, another is a target domain. And in the network training, we have the training image from the source domain and the target domain, but we only have annotation on the source domain. So the target domain image is unlabeled. And we want to train a network to achieve better performance on the target domain. So this is the setting of domain adaptation. And we propose the 2 methods to solve this problem. And the general idea of these 2 methods are very simple because in the input space, we can see there have some appearance or difference among the images from different domains. But in the output space, that means the optical disc and the cup segmentation maps, they have some similarity. So based on this similarity, we propose the output space adversarial learning strategy. That's the key idea of this method is we use a discriminator to encourage the network generate very similar prediction for the image from source domain and the target domain. And the following figure shows an improved version of this method. And in this case, we also calculate the boundaries and the entropy map. We also use the adversarial learning strategy to encourage generate the similar boundaries for the image from the source domain image and the target domain image, because generally the network would generate a very bad result on the boundary region. So we especially enforce the network generate the similar boundary for the source domain image and the target domain image. And another very similar setting is domain generalization. Because in domain adaptation, we need the unlabeled target domain in the network training. But in some cases, it is impossible to get the unlabeled target domain because we don't know what image this software or algorithm would handle with. So in this case, we studied the domain generalization problem. In domain generalization, the basic setting is in the network training, we have multiple source domain dataset, and we want to train a segmentation network. After we training the segmentation network, this network can directly test on the unseen target domain, and we also want to achieve very good performance for the unseen target domain. So this is the setting of domain generalization. And the key idea of domain generalization is study how to learn a general feature from the multiple source domain. And in our recent work, we propose a feature augmentation-based strategy. And we also study it is possible to combine the self-supervised learning to the domain generalization. And so in our two papers, we show it is possible by utilizing the self-supervised learning to improve the generalization of the features. And we also show it is possible to utilize the feature augmentation to improve the generalization. And lastly, I will briefly introduce our recent work on incorporating domain knowledge into AI models for medical image reconstruction. Actually, the medical image reconstruction is a long-standing problem. For example, the CT image reconstruction aims to reconstruct the tomographic image from the X-ray projection. So this figure shows the geometric view of the X-ray source, patient, and the projection. And this is for 3D cases. And for the 2D cases, the projection data compose the sinogram. And we want to reconstruct the original CT slides from the sinogram data. Since this is a very long-standing problem, there have lots of analytical-based methods for this problem, like the FBP, field bank projection. So from mathematical view, the FBP can actually reconstruct the CT image from the sinogram data. But due to some noisy or other issues, generally the FBP is difficult to achieve very good performance. And in this project, we aim to develop the domain knowledge enhanced deep learning systems for this problem. Specifically, we wanted to combine this physical model, that is the FBP, into deep learning system to improve the generalization of the quality of the reconstruction. And the specific application is mental artifact reduction, because the patient would often lead to mental in place. And these mentals would lead to unreliable projection in the sinogram. So if we directly reconstruct the CT image from the sinogram, it would lead to very strong artifact. And the traditional method solve this problem using interpolation. They regard the unreliable projections as missing, and using the interpolation method to estimate the projection values so that they can get a corrected sinogram. And the final corrected image is FBP reconstruct from the corrected sinogram. And recently, there have some deep learning-based method, but this method directly regard it as an image post-processing problem. They take the mental artifact image as input and directly regress the mental free image. However, the interpolation-based method would often lead to secondary or new artifacts in the final image, since it is difficult to get corrected sinogram, and the deep learning-based method is very difficult to generalize to new cases because this is a data-driven based method, and there is no physical constraint for the network output. And in this project, we want to develop a generalizable framework for mental artifact reduction by incorporating the domain knowledge, specifically the FBP or BP models, into deep learning framework. And we formulate this framework as a prior image-based sinogram computation. Specifically, given the original sinogram data, we first use an image domain network to generate a prior image with less artifacts, and then we follow the project to get a prior sinogram. And with the guidance of the prior sinogram, we use another sinogram domain network to restore the missing data with the guidance of the prior sinogram so that we can get a very correct sinogram. And the final image is FBP reconstruct from the corrected sinogram. And the whole framework is end-to-end training. Because the final image is FBP reconstruct from the corrected sinogram so that we can ensure the physical constraint of the final image. So we can say generally our framework combines the merits of deep learning based method and the traditional based method. And this figure shows the sinogram completion result. This is the original sinogram. This is the ground truth. This is the interpretation-based method. So we can see generally the interpretation-based method generates very poor estimation compared with the ground truth. The deep learning-based method generates a good result than the interpretation-based method. And with the guidance of the prior image, our result can generate a more better result. And this is the final result. So from the zoomed in punches, this is the original image without a mental artifact. So this is the ground truth. This is the mental image with the mental artifact. C to H are the result of different result. H are the result of our method. So compared with the ground truth, we can see our method can better preserve the anatomic structure of the spine. And we also achieve the better quantitative result. We also apply it to the head CT image. We can see our method can also generate a reasonable result for a different set image. And this is the result on the real clinical image. From the yellow zoomed in punches, we can see our method can preserve the fine details of the anatomic structure, while the other method would change it. So until now, I have discussed my research on designing deep learning technology for medical imaging tasks. We can see deep learning is rapidly playing a critical role in medical imaging tasks, and it is very promising to improve its generalization of the whole system by designing some data efficient learning algorithm to overcome the limited training data set or incorporate the domain knowledge into AI systems. However, there are also many challenges for the deep learning or AI-based medical imaging tasks, like how to integrate AI solutions into clinical workflow, and this needs collaboration between doctors and other researchers. And for the future research, I think the following directions are very promising. One is the trustable, generalizable, and explainable system. Because generally, the deep learning system give a prediction from the input medical image data. But for the safety critical medical imaging task, we also need to know why the model gave the prediction and its confidence. So that it is very promising to develop trustable and explainable systems for medical imaging tasks. And this is related to several machine learning sub-areas like the transfer learning, domain adaptation, mental learning, or network interpretation. Currently, we have conducted some framework on this topic like multi-set learning, mental learning for rare disease diagnosis, and learning from noise label. Another very promising is how to incorporate the multi-modality data, because in real clinical routine, besides medical image, we have medical document, molecular data, and genomic data. So how to combine these different data medical data to develop models for early disease diagnosis and treatment is another very interesting topics. And lastly, we can also explore how to apply the AI for other healthcare problems, like how to handle with different biomedical data, and how to process the electronic health record, and another very promising direction is the mobile health, because currently we have wearable device and we have lots of data, and how to handle of analysis data set is also very promising. Okay, this is my presentation, and thanks for your attention, and I welcome your questions.
Thanks, Lequan, for the interesting talk. I guess we have quite a few questions here. Okay, so Xiaochen, you want to kickstart?
Hi, may I have a question, please?
Yes, please ask.
Okay, so in the beginning, you said about uncertainty estimation. Can you please explain more about that? Can you you quantify the uncertainty, or somehow you have uncertainty map? How did you build the map? Yeah.
So actually, we want to estimate the uncertainty map. So in our implementation, we use the predictive entropy as our uncertainty map. So generally, this is the entropy. And but we also use the Monte Carlo dropout to get the several predictions, and then we calculate the mean prediction from the several prediction and calculate the entropy.
I see. Okay, thank you very much.
Yes, thank you.
Okay, do you have any other questions? So there's a question in the chat.
Okay.
May I know your view on what would be the direction for this deep learning interpretability research? Thank you.
So generally, besides the medical image, or in generally the deep learning research, the interpretation is a very important direction. So currently there have some work focused on designing the attention-based methods, wanted to use the attention map to get some interpretation. But I think one of question of network interpretation study is, how do you evaluate your interpretation is correct? Because currently there is no ground truth, or no one know what is the true interpretation and what is the false interpretation. So maybe this is another challenge. This is the one challenge. And I think another maybe possible solution is like incorporate the domain knowledge or domain rules. Because if we incorporate the domain rules into the network, we can explain the prediction or the results from some aspect. So I think.
But I think for this deep learning segmentation, right, we really can see the results. You know, I mean, in that case, if we see the result, we know it's accurate or not, right? In that case, it's kind of interpretable of your results, right? But in terms of how can we explain, I mean, what happened inside the network, it might be still a little bit difficult at this moment. In terms of fully understand what happened.
I think this is also a very good point of view. For the segmentation, we can see what is the ground truth, or we can see where the network is good on. But for some diagnosis, for example, desired some disease from the image. So actually, we want to find the biomarkers, but it is difficult to understand why the deep learning makes such prediction, or whether what biomarkers are the deep learning relied on.
Yeah, good. So I have a question related to this image translation, right? So I know the image translation now is doing very well. If we only consider appearance, right, or intensity distribution, we can transfer one intensity distribution to another one. But how do you guarantee this structure? So I mean, if do you understand my question?
I understand your question, because so in this we only want to change the intensity. We don't want to change the anatomic structure. So actually you can see, because this is a segmentation network, that means After we translate the image, we also feed to a segmentation network. And the segmentation network actually have a ground truth. This ground truth is from the MRI because the MRI is labeled. So that we have the anatomic, we have the ground truth.
Okay, I see. Yeah.
So it looks like we use a segmentation network to provide the anatomic constraint for the translation.
Sure, I got you, yeah. And another question is, you combine, in terms of this CT reconstruction, you said you combine this deep learning and a physical model, right? How about this inference time? Is it slow or is it like as fast as you do direct UNet reconstruction, for example?
Yeah, I understand, because in the testing, we also need to conduct the forward projection and the backward projection.
Yeah.
So it is a little longer than we only use the deep learning. But since the FBP has well implemented in current libraries, so that the time is not very long.
Okay, yeah, that makes sense. Okay, do we have any other questions? Okay, good. If we don't have any further questions, I think we will end today's talk. Thank you for all coming.
Yes, thank you.